Hello everyone, this is Dr. Fan. Today let's discuss a question about friction. This is my go-to question to test my students' understanding about friction. If you understand how to solve this question, you should be able to solve the majority of questions about friction. Alright, let's look at this question in detail. The setup of this question is very simple. There is a small block of mass m, which is placed on a large block of mass 5m. Both the static friction and the kinetic friction coefficient between the blocks and between the block and the ground are mu. So the friction coefficient everywhere is mu. And the question asks, what is the minimum applied force so that the two blocks will slip? There are two setups. On the left, there is a string. On the right, there is no string. So there is this tiny difference here. If you think you can solve this question, you can pause here and write down your answer and check if your answer is correct. Alright, now let's work on this question together. Before we work on this question, I want to remind you, friction is a force that resists relative motion, right? So if you have actual relative motion, then you have kinetic friction. If you are resisting potential relative motion, then you have static friction, right? We know the kinetic friction equals to mu k times the normal force. And we know the static friction force is smaller or equals to mu s times normal force. With all this knowledge, we should be able to tackle these two setups. Alright, let's look at the left one, which is easier. So if there's a force F pulling onto the right, then this lower block have a tendency to move to the right. So there is a relative motion to the right. Then what's going to happen? The ground wants to provide a friction that resists this motion, and this is the friction from the ground. At the same time, the upper block also wants to resist this motion, so there is a friction force from the block. As a reaction force, the lower block also gives the upper block a reaction force, F block prime. So this force here and this force here, they are action-reaction pair. So because the existence of this string, we know this upper mass is not going to move. So if we want these two blocks to slip, then as long as the lower block moves, then they're going to slip. So now we just need to find out when the lower block is going to move. If the applied force is larger than these two resistive friction force, then the lower block should be able to move to the right. So the condition should be when F is larger than the friction from the upper block, this force right here, plus the friction force from the ground. And we know these are the static friction force this applied force needs to overcome. And the static friction force should be smaller or equals to mu s times the normal force. And for the friction force from the upper block, we know this static friction force should be smaller or equals to mu s times the normal force. And we know the normal force here, Fn equals to mg. So the maximum static friction force should equals to mu mg. And that's from the upper block. Then we know the friction force from the ground should also be smaller or equals to mu s times the normal force. And we know ground provides a normal force of 6 mg. So the maximum static friction force from the ground equals to mu 6 mg. In other words, is 6 mu mg. And if we plug these two forces into this upper equation, we know the applied force should be larger than mu mg plus 6 mu mg. So the condition is when the applied force is larger than 7 mu mg, the lower block is going to move to the right, so the two blocks are going to slip. So this is the condition for slip for the left setup, which is a simple situation. Now let's look at the setup on the right. For the right setup, there is no strain. And when this applied force is pulling to the right, this lower block has a tendency going to the right. So there is a potential relative motion. So the ground will provide a friction force here. But will the upper block also give a friction force? The answer is it depends. Why? Because if the applied force is small, let's say the applied force is smaller or equals to 6 mu mg, which is the maximum static friction force the ground can provide. In this case, the friction force from the block should be 0. Why? Because if this upper block gives this lower block a friction force, as a reaction force, this lower block also gives this upper block a force equal in magnitude but opposite in direction. But if this applied force is not large enough to overcome the friction force from the ground, this lower block is not going to move. So the upper block should also not move. But if this friction force exists, there is a reaction force here, and that's the only force on this small m. So this small m would move to the right if this friction force exists. So that's why when the force is small, when it's smaller than 6 mu mg, the friction force from the upper block should be 0. Now, what if F is larger than 6 mu mg? In this case, the applied force overcomes the friction force from the ground. Then the friction force from the upper block will kick in. And this friction force from the block wants to resist this potential relative motion. And this friction force wants to keep small m and 5m, these two blocks, moving at the same acceleration, so they will not slip. As you can imagine, as F gets larger and larger, this lower block will move faster and faster. So this lower block would have a larger acceleration. But this friction force between the small m and 5m, there's a limit. We know this friction force here, F block, the friction force from the upper mass to the lower mass, is going to be smaller or equals to mu mg. And this is the only force applied onto this upper block. So based on Newton's second law, net force equals to mass times acceleration. This is the maximum force applied on this upper mass. So if we let this upper mass have this largest force, then we basically get the maximum acceleration for this upper mass. So that means for this upper block, its maximum acceleration is mu g. If the acceleration of the lower block is larger than mu g, then the upper block cannot catch up. Then they will slip. So then how do we determine this critical force? That's very straightforward. We know this critical force happens when the lower block and the upper block moves with this maximum acceleration. So if we consider small m and 5m as a whole system, then we know the net force on them equals to the applied force minus the kinetic friction from the ground. Because now small m and 5m, they're gonna move together to the right. So there is relative motion between the lower block and the ground. So this becomes a kinetic force. So F minus the kinetic friction force from the ground, and that equals to the total mass small m plus 5m, and then times the maximum acceleration. And we know the friction coefficient is mu, so this friction force is 6 mu mg. So this equation becomes F minus 6 mu mg equals to 6m times the maximum acceleration mu g. Then we get this critical force F equals to 12 mu mg. That means for the right system to slip between the two blocks, your force needs to be as large as 12 mu mg. And under this situation, the friction force between the ground and the lower block is kinetic, and the friction force between the small m and 5m, they are static because they don't have relative motion. They are moving at the maximum acceleration possible without slipping. So for the left system, the minimum force is 7 mu mg, but for the right system, the minimum force is 12 mu mg. Did you get it right? We can also rationalize why the right system has a much larger force. It's very easy to understand because on the left there is a strain to pull. This upper block on the left system cannot catch up with this lower block. But for the right system, because there's no strain, the static friction force between these two blocks are able to let them move with the maximum acceleration as large as mu g. Hope that this question helps you to understand the friction better, and I will see you next time. Thank you.